What I'd like to describe in this video is the theory and application of standing waves on a string. So standing waves could describe things like the vibration of a string on a violin. When you pluck the string or bow the string, these waves will be caused to happen on the string that look like that or just like that. So we're going to get different patterns depending on how you bow the instrument and where you put your finger. These are called standing waves because the waves don't seem to be moving anywhere. There's an illusion that it's not really moving, but as a matter of fact the waves are moving. So one way to think about a standing wave being formed is by thinking of it as two oppositely moving waves. So I have a wave moving to the right with the wave velocity given by omega over the angular frequency of the wave divided by the wave number of the wave. So these terms were defined in the basic video on waves earlier. And then there's a left moving wave with the same speed but in the opposite direction. And the right moving wave and the left moving wave are offset by half a wavelength. So this entire distance from top to top is one wavelength. So if you offset it by half a wavelength, you get this picture like this. Now if I bring these two together and make them coincide, then I'm going to get a pattern that looks kind of like this. And that pattern is called a standing wave. Okay, you'll notice that you end up with these objects that are about half a wavelength in length, and they look like closed loops, or I like to call them melons because they appear like little watermelons. So you get these melons, and when you have that, you're said to have a standing wave. But mind you, it's not really standing. The wave is moving like this and like this at all times. It just appears to give the illusion that it's going nowhere, and it's just like that. Now if you trap this wave between 2 points, now in a typical application in a musical instrument like a guitar or a violin, there's one end that's attached to the tuning pegs and the other end that's attached to the bridge. So if you have those two types of obstacles, or in a more simple example, you have a clothesline, let's say, and here I'll draw the n equals 3 case. So when I say n equals 3, I'm counting the number of melons, okay? So this would be the n equals 3 case. So there are 3 of these things. The technical name for a melon is called an antinode. So physicists don't really call it a melon, they call it an antinode. More precisely, the antinode is the maximum distance in one of those melons, okay? So if there are 3 of these antinodes, then I'll call that n equals 3. Now the points where it attaches to the support, like for example a clothesline with 2 walls on either side, these are called anchor nodes. You don't count them because they are only suitable for anchoring the string or the clothesline. Okay, now you have 3 antinodes, and in between 2 antinodes you have what's called a node. And these nodes are always, they're not vibrating at all. They're just there in space, not moving. And the antinodes are vibrating to the maximum degree. So let's try to figure out the relationship between wavelength and frequency of each of these nodes for different values of n. Let me try n equals 1 first. The simplest, I drew n equals 3. So let me draw n equals 1 now. N equals 1 will be the simplest case. You just have one single antinode. So that would be a half a wavelength, lambda over 2 for n equals 1 would be equal to the entire length. So I'll call this the length of the string, capital L. So which means that lambda 1 is 2L. All right, let's try n equals 2 now. If you try n equals 2, then you have to have one node in the middle, so I like to draw this node first, so I'll know how to draw the rest of my figure. So I do that, and I get this one node in the middle. This time I notice that an entire wavelength, so lambda 2 is equal to L, or to make it look like that, I'm going to write it as this as 2L over 1 and this as 2L over 2. You'll soon see why I'm doing that. Let's go back to n equals 3, which is up here. There I'm going to have lambda 1 over 2, half a wavelength, is 1/3 L, which means lambda 3, excuse me, lambda 3. So lambda 3 would be 2L over 3. You're seeing the pattern here. Lambda n is going to be 2L over n. And once you have lambda n, you can find the speed of the wave. The speed v that I have here is just given by lambda n times the frequency fn by the wave relation. So you can find the nth harmonic frequency fn for this particular string is given by that. Now later on I'll tell you what the velocity is given also by, but right now let's just save this. Let's try to describe this whole thing mathematically, because so far I've just drawn pictures and called things melons and such, so it doesn't seem very rigorous way to do this. But actually there's a very nice mathematical description of this entire problem using the wave equation that we have and the process called wave addition or wave superposition, the fancier name for addition. So what we're going to do here is to describe this right moving wave mathematically. Now you know that for a wave moving to the right, y of x comma t is going to be a cosine of kx minus omega t, plus a phase factor, which I'm going to ignore in this case. I'll just say the phase starts at 0. The phase is adjusted to be 0, so we don't worry about it. Now that's the top wave, so I'll call that y1. That's what y1 is. y2 would be the bottom wave. Now remember, y2 is first of all flipped down, so you have to put a negative sign. And then it's also moving to the left. Now if it's moving to the left, you're going to get a plus sign between x and kx and omega t. You should really see the video on wave equation basics, part 1 and 2, to understand why the right moving waves have a minus sign and left moving waves have a plus sign. So if I add these two mathematically, I would be getting this picture. So let's try that. Y total equals y1 plus y2, and I will end up getting a cosine kx minus omega t minus cosine kx plus omega t. How do you deal with this? Actually, if you remember something about trigonometry from your pre-calculus classes, you will probably know what to do next. They are the addition formulas for cosine. So I'll write them here. Cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. You can certainly go somewhere and find the proof of this. It's pretty nice. I'm not going to bother proving it. I'll just use these results. Cosine alpha plus beta is similarly cosine alpha cosine beta minus sine alpha sine beta. Now this is exactly set up like that, except alpha would be this and beta would be that. Alpha is kx and beta is omega t. So I'll just apply this word for word, and I end up getting here. So let's see, cosine alpha cosine beta plus sine alpha sine beta, and when I subtract it, these cosine terms will cancel out and the sine terms will add. So I'm going to get 2a sine of alpha, which is kx, times sine of beta, which is omega t. So that's a pretty remarkable formula, because it shows us that space and time are decoupled. So The decoupling of space and time is what gives this wave the appearance that it's not moving, it's just standing there. So if you look at the violin that's being bowed, the violin is not exactly going places, it's just standing in one place, and the string appears to be just vibrating like that in one place and creating this huge amount of sound. And that's the origin of that phenomenon. Now, how do we talk about the anchor nodes? The anchor nodes are enforced by what is called a boundary condition. So we have to apply two boundary conditions. The first boundary condition is that the left end is fixed, and so I'll write that as yt. This would be yt as a function of x and t here. So let me write the first boundary condition, and on the left end is fixed means x equals 0 is fixed for all time, and that is 0 because that end does not move. This y describes the displacement from the equilibrium in the vertical direction. Well, there's no displacement here and there's no displacement there, and that's what we're trying to enforce here by boundary conditions. So y of 0 comma t is 0, and that tells us that 2a sine of 0 times sine of omega t is 0. Well, sine of 0 is always 0, so that's easily satisfied. There's no trouble satisfying that. Yt is also 0 at the other end, at L. Well, what does that give us? You get 2a sine of kl times sine of omega t. Now, if that has to be 0, you cannot have sine omega t equals 0, because then you'll be choosing a special time and you're not allowed to do that. So the only option you have is to choose sine of kl to be 0. Kl has to be not necessarily 0, but any multiple of pi, including 0. So n equals 0, 1, 2, and so on. So that's the solutions for this. N equals 0 does not give us a very good standing wave, because if n equals 0, then k will be 0, and this entire wave will be a degenerate object. It's not moving at all. So that's the degenerate solution, and we don't keep that. Other than that, all these values are allowed. Let's see what we get. K is equal to 2 pi over lambda. Don't forget that from your wave basics. So that's equal to n times pi. Well, let's call this lambda n for the nth harmonic. So the pi's cancel out, and lo and behold, I get this very formula here. Lambda n equals 2l over n. So whatever I got from this intuitive picture, I'm getting through solid mathematics. So that's a very nice situation indeed. It's always nice when complicated mathematics jives with what you expect just by thinking about things. The last item of order is to tell you about the speed. Now, if you've ever played a musical instrument, you know that in order to make the pitch higher, you have to tune the pegs and make the string tighter. So somehow the tension in the string seems to increase the frequency, and increasing the frequency can only happen for a given wavelength if you can increase the speed. So the speed must be related to the frequency. The actual theory of this is kind of complicated, and I won't go through it. I'll just give you the formula. The speed in a string that is stretched is given by the square root of the tension in the string divided by a quantity called mu, and mu is the mass of the string divided by the length of the string. I've been very careful in my previous theory to call friction coefficient mu sub k or mu sub s. So please don't confuse this with friction coefficient. It's a completely different object. It's mass per unit length with units of kg per meter. Actually, at least let's see why unit-wise this formula makes sense. So let me find the units underneath this formula. Well, force is measured in newtons, and mu is measured in kg over meters. Newtons by F equals ma is kg meters per second squared, and this is kg over meter. I get rid of a kg. That meters goes upstairs, and it becomes meters squared per second squared, and that is meters per second. So it does give us what you expect in terms of dimensions at least. Now the actual formula requires a bit of work to derive, and I think I do it in my fact sheet number 24 for those who are interested in the full-blown theory of that formula. So once you have this, you can actually play with this equation and that in a very nice way. You can write the equation that lambda n, the frequency of the nth harmonic, would be equal to the speed times n over 2L. So n over 2L times the speed, which is the square root of ft over mu. So that's the formula that gives you the frequency of a violin string, the nth harmonic of a violin string, whose mass per unit length is mu and whose tension is ft, and n is the order of the harmonic. 1 is called fundamental, 2 is called the fundamental of the first harmonic, that's called the second harmonic, that's called the third harmonic, and so on. So that's the theory in a nutshell.